Welcome to aminacademy.com. In physics, let us discuss about capacitance and capacitor. What is capacitor? Capacitor is a device that stores energy. Often, although certainly not always, it consists of two conductors separated by an insulator or dielectric. The capacitance C of a capacitor is defined as capacitance charge over potential difference. It is in farad. So the unit is farad. Farad means capacitance by potential difference is the unit is farad. Q by V, we can say it's a Q by V. Coulombs per, which is equal coulombs per volt. Coulombs per volt. The ability of the capacitor to store charge is known as capacitance. Capacitors store energy by holding apart pairs of opposite plates that is charged. The simplest design of a capacitor is a parallel plate which consists of two metal plates with a gap between them. Next, we define what is capacitor. A capacitor is a two-terminal electrical device that can store energy in the form of an electric charge. It consists of two electrical conductors that are separated by a distance, some particular distance. The space between the conductors may be filled by vacuum or within an insulating material known as a dielectric. This is different types of capacitors available in market. Next, we'll define parallel plate capacitor. A parallel plate capacitor here are the type of capacitors that have an arrangements of electrodes and insulating materials, that is dielectric. The two conducting plates act as electrodes. There is a dielectric between them. This acts as a separator of the plates. Dielectrics in between the plates act as a separator of the plates. The two plates of a parallel plate capacitor are of equal dimensions. They are connected to power supply, that is positive and negative terminals. The plate connected to the positive terminal of the battery acquires a positive charge. On the other hand, the plate connected to the negative terminal of a battery acquires a negative charge due to attraction of charges or in way trapped within the plate of a capacitor. A multi-plate capacitor, also known as a multi-layer capacitor, MLCC, that is multi-layer ceramic capacitors, for example, is a type of capacitor that consists of multiple layers of alternating conductive and insulating materials, like here. Further, parallel plate capacitor we discussed, that is capacitance. Here, the capacitance C equal K into epsilon 0 A over D, where K is a dielectric constant epsilon 0 is permeability in vacuum, A is the area of the plate, and D is the separation distance between the plate. Here K equal epsilon over epsilon 0, and here where epsilon 0, the constant is 8.85 into 10 raised to minus 12 C square over Newton meter square, or Farad by meter, which is further equal Farad by meter. For vacuum, K equal to 1. For vacuum, K equal to 1. Some other thing, other dielectrics, it varies. Capacitors, next is capacitors in series and parallel, we will discuss. Capacitors can be connected in series way or parallel way. Capacitors in series and parallels may be discussed down. Capacitors may be connected in series or in parallel to obtain a resultant value which may be either the sum of the individual values in parallel or a value less than that of the smallest capacitor in series. First we will discuss about capacitors in series. Look at here. Look at this figure. These capacitors are connected in series. That means what? Positive terminal, negative terminal, and alternatively negative terminal, positive terminal of the second capacitor, and that capacitor is connected. Voltage is supplied the outer terminal. The circuit consists of number of capacitors in series is similar in some respect to one containing several resistors in series. In a series capacitive circuit, the same displacement current flows through each part of the circuit. Here, voltage is distributed, but current is same flow through. Flow through each part of the circuit, and the applied voltage will divide across the individual capacitors. Here, same displacement current flows through each part of the circuit, and the applied voltage will divide across the individual capacitors. The figure shows clearly here. Now, the sum of the capacitor voltage must be equal to the source voltage, that is Kirchhoff's voltage law. That is V equal distributed V1 plus V2 plus V3. The sum of three voltage is equal to main voltage. The charges on all capacitors must be the same. Charge of the all capacitors is the same. Since the capacitors are connected in series, and any charge movement in one part of the circuit must take place in all part of the series circuit. That is, we have C equal to Q over V, the formula for voltage in terms of capacitance and charge. The following results are obtained for each of the series capacitors and total capacitance. We know that V equal Q over charge is in C1, capacitor 1. V2 equal to Q by V equal to Q by C total, and V1 equal to Q by C1. Q is not changing. V2 equal to Q by C2, and V3 equal to Q C3. Now, here Q by C total is total capacitance equal to Q over C1, Q over C2, Q over C3. Then take out common Q and cut the remainder things is 1 over C1, 1 over C total is equal to 1 over C1, 1 over plus 1 over C2 plus 1 over C3. This is a reciprocal of total capacitance is each reciprocals of capacitance and added. Therefore, taking the reciprocal of both sides and assuming any number of capacitors. So in general, C total in series circuit equal 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn. This is the formula for total capacitance in series circuit. If there is only two capacitors, C total is C1 C2 over C1 plus C2. That means simply here 1 over C1 plus 1 over C2, take LCM C1 C2, then cross multiply C1 plus C2. Now capacitors in parallel. When capacitors are connected in parallel, look this figure. One plate of each capacitor is connected directly to one terminal of the source, while the other plate of each capacitor is connected to the other terminal of the sources. In the figure below, all the negative plates of the capacitors are connected together and all positive plates are connected together, and the total equivalent capacitance CT therefore appears as a capacitance with a plate area equal to the sum of all individual plate areas. As previously mentioned, the capacitance is a direct function of a plate area. Connecting capacitors in parallel effectively increase plate area and thereby increase total capacitance. Here, capacitors in parallel will derive. We know that capacity total is Q total over V. In this, in parallel plate capacitors, there is no voltage change. Each voltage is same for each capacitor. Therefore, Ct equal to Qt over V. C1, first capacitance is equal Q1 by V. Second capacitance is C2 equal to Q2V. C3 is Q3V. Now, then take addition of these things. That look at here. C, we know that Qt total charge is Q1 plus Q2 Q3. Substituting Q1, then from the equation C equal to Q over V, then Q equal to CV. From this, by cross multiplying, Q equal to CV, then substitute each Q, that is CTV equal, that is QT total equal to CTV, CTV, and C1V plus C2V, C3V. Take out V common and here V cut, and therefore C equal to C1 plus C2 plus C3 plus Cn. Look at here that CTV equal V bracket C1 plus C2 plus C3, then V and V cut, therefore which gives C total is C1 C2 plus C3. If number of capacitors increase, that C total is also increased, that is C1 plus C2 plus C3 up to Cn. This equation states mathematically the total capacitance of a capacitor in parallel is the sum of all individual capacitors. So far we discussed about what is capacitor, capacitance, and capacitors in series and parallel connections, what is parallel plate capacitors, and what is multi-plate capacitors. We have done. Please subscribe our YouTube channel.